Hey everybody, we're back at it with video number 2 for Taylor series intro. We just found a second degree polynomial approximation for e to the x. I want to get even better than that, and I want to try getting a fourth degree polynomial, and I'm going to do it a tiny bit differently with the way I write my coefficients so we can see a pattern better and write a general rule using n's for c sub n, not like c sub 0 or c sub 1. So we want a polynomial, so you're always, even if you're not just doing e, like let's say you're doing sine or cosine, you're always going to start out with this general polynomial to whatever degree you want. I'm going to degree 4 because I want p sub 4, polynomial of the fourth degree. So I need to find these coefficients. These coefficients will personalize my polynomial to the function I'm doing, which in this case is e to the x. So let's go through the first one quickly because we just did them. And you're probably thinking, we just did this, why are we doing it again? And it's because you are just learning this and the first few seeing again will kill you. So I need to find p sub 4 of 0, no derivative here. If you evaluate our fourth polynomial at 0, all these 0 out, it was just c sub 0. F of 0 is e to the 0, which is 1, so that's how we got c sub 0 is 1. P prime sub 4 of x was c1 plus 2c2 of x plus 3c3x squared plus 4c4x cubed. F prime of x is e to the x. P prime sub 4 of 0 is all of these 0 out. Any term with x zeros out is just c sub 1. F prime of 0 is e to the 0, which is 1. C sub 1 equals 1. Okay, P double prime sub 4 of x is derivative of a constant is 0. 2c sub 2 plus, okay, pause. Normally you would say, okay, that's 6c sub 3, but hold on, write it like this. You'll see why in a moment. Plus 4 times 3, c sub 4 x squared. Normally you'd say, oh, that's 12, but just follow along. F double prime of x is e to the x. P double prime of 4 of 0 plugs 0 into my polynomial approximation. Everything zeros out plus 2 except for 2c sub 2. F double prime of 0 is e to the 0, which is 1. 2c sub 2 is 1, meaning c sub 2 is a half. Those are my first 3 coefficients. So I'm done with this one, and this one. I still have these 2 to go. So moving on up here, let's keep going. This is new. Okay, so p triple prime, my third derivative of my fourth degree polynomial, is 2c sub 2 is gone. 3 times 2 c sub 3x plus, watch this, 4 times 3 times 2 c sub 4 of x. My third degree function is e to the x. Evaluate your third degree, evaluate your third derivative, fourth degree polynomial at 0, and it's 3 times 2 c sub 3. Hold the phone. There should not be an x there. Sorry. Because the derivative of this term is just the coefficient. Derivative of x is 1. Sorry about that. So when I plug 0 into this goes to 0. This is just the same. My third degree function at 0 is e to the 0, which is 1. Now I'm going to set my polynomial approximation equal to my actual function value. So c sub 3 is 1 over 3 times 2. Let's do one more. Start looking for patterns here. You can't do these mindlessly because you got to start picking up patterns for all of these series. My fourth derivative. Now I don't feel like writing 4 tick marks because that's messy, and if you don't write clearly it could look like a fifth or a third degree. So remember this notation. Whatever's in your parentheses up in the exponent is the number of derivatives you've done. Okay, derivative of this is 0. The derivative of this is just the coefficient. 4 times 3 times 2, c sub 4. My fourth derivative of f is e to the x. Again, surprise. P fourth derivative of p sub 4 at 0 is just this. There's no x to plug into. And the fourth derivative of f at 0 is e to the 0, which is 1. So set your polynomial value equal to your function value. 1 over 4 times 3 times 2. Now, if you did stats, you definitely have seen this, but I'm pretty sure every one of you has probably seen this. I want you to look at your coefficients, especially these two, and think of how you could rewrite your denominator. Like instead of saying 4 times 3 times 2, what's another way we can write that? And hopefully you've seen something called a factorial before. A factorial, let's say I did n factorial. That would be n times n minus 1 times n minus 2 dot dot dot. More generally, 5 factorial is 5 times 4 times 3 times 2 times 1. So 4 times 3 times 2, there's actually a times 1 there. C sub 4 is actually 1 over 4 factorial. C sub 3 is actually 1 over 3 factorial. 3 times 2 times 1. C sub 2 is actually 1 over 2 factorial, because 2 factorial is 2 times 1, which is 2. C sub 1 is actually 1 over 1 factorial. C sub 0 is actually 1 over 0 factorial, because 0 factorial is actually 1. So let's take all of these. Make sure you wrote the factorial version next to each of these, because that's what we actually want. And let's rewrite our polynomial. What we can do now is we can take our general polynomial, p sub 4 of x, for any series, and we're going to replace all our coefficients with what we found our coefficients to be. By replacing our coefficients, we are personalizing the general Taylor series, or the general series, and making it specific for e to the x. So notice I put my factorial terms here. This is p sub 4. If I want just a general infinite series for e to the x, I would just put plus dot 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 at the end. And this is actually e to the x as an infinite series. So what you'll see in textbooks is this. Like we already did, remember, f of x, which is 1 over 1 minus x. It was 1 plus x squared plus x cubed plus dot dot dot. E to the x, what you'll see is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and you can keep going. And then you'll see this, plus dot dot dot. You need to be able to write the general term with n. So just keep following the rule. It would be x to the n over n factorial, because whatever the exponent is, that's what the factorial is. This right here is the general term. Partial or parts of the free responses will often ask you what the general term is. And then they might even ask you to write the series notation for e to the x. Well, let's use n because I think you guys decided you like n a little bit better. If I start at 0 and I go up to infinity, it would be x to the n over n factorial. Again, this is just for e to the x. So if you test it, plug in 0, x to the 0 over 0 factorial is 1. Plug in 1, x to the first over 1 factorial is x. If you keep plugging in higher and higher numbers in here, you'll get this. So make sure you write those two down. One thing I want you to realize is that when we did e to the x, all of the function values were 1. And the reason I'm putting f to the n degree in parentheses is this means all the derivatives of f. So not only just f of 0, but f prime of 0, f double prime of 0, f triple prime of 0. And just to verify that, let's look, come on buddy, up here. All of my f's, no matter what degree or what derivative I took, they were all 1, which is why I was able to write my coefficients all with a 1 in the numerator, because the function values, like I said, were all 1. That is not going to always happen. It happens for e, but not always. So we could write 1 over, where did it go? All my coefficients for e were in the form 1 over n factorial. But like I said, that's not always going to happen. Sometimes your f to the nth degree of 0 will be something else. And we don't know what it's going to be yet because we haven't done the other series. But in general, your coefficients, instead of being 1 over n factorial, it'll be whatever the function values are at 0 for different derivatives of f. So more generally, your coefficients will be in this form. And this is for any Taylor series. Very important you know this. This is something you kind of have to have memorized. So this is the rule to find any coefficient. Again, this was for e to the x specifically, because all the function derivatives at 0 were 1. This is for any Taylor series that we're going to do, like for sine, cosine, square root, ln, all that stuff. So I can write the series, which I had written up here, more generally for any series. I'm going to write it like this. So my function is going to be the sum from 0 to infinity of my coefficient times x to the n, where my coefficient is defined to be what I just wrote above. the function at the nth derivative at 0 over n factorial. If you want to combine these two, it kind of bothers me writing them separately. If you want to go ahead and put c sub n where c sub n is right here, then you can condense it into one form. So this is how we write a polynomial Taylor series for any function. Okay? Now let's go ahead and do this for another one. One thing to realize though before we get to cosine is two more vocab words here. We've been centering at x equals 0. If our Taylor series is centered at 0, remember centering is where the tangent line is. If I center at 0, it's called a Maclaurin series. A Maclaurin series is a type of Taylor series where we center at 0. So that means everything we've done so far is a Maclaurin series. If you center anywhere else, it's a Taylor series. So if you center at like x equals a, it's a Taylor series. Now let's say we center our series at a instead of at 0. That means we're shifting horizontally to a from 0. And think back to like algebra 2. If I had x squared, it looked like that. If I had x minus 4 squared, I would move 1, 2, 3, 4. Putting something in parentheses just shifts it left and right. So instead of writing the sum from 0 to infinity of c sub n x to the n, what we're going to write for a Taylor series more generally is c sub n x minus a to the n. So what I'm going to do is what we had written above, which is c sub n x to the n, and wherever there was an x, I'm going to put the horizontal shift in. Same thing, just shift it. That means my coefficient, which was f to the nth derivative at 0, is f to the nth derivative at a. If I want to combine those two statements into one, it's going to look like this. This is for a Taylor series. Taylor series centered at a. Okay, so the only other thing we have to do real quick is get cosine. Last thing I'm going to show you how to do is to get the Maclaurin series, again just a Taylor series centered at 0 for f of x. This is series number 3, so we're working our way through the ones we need to know. There's 4. You're going to do sine for homework, so make sure you're following along with cosine. I'm starting with the general polynomial p sub 4 of x. My job is to find the coefficients. That is going to personalize my general series for this specific cosine of x. Now remember, we already did this for 1 over 1 minus x, and e to the x, we got these two, which need to have memorized. Let's go ahead and find what the coefficients are for cosine. So my p sub 4 of 0 is c sub 0. F of 0 is cosine of 0, which is 1. So c sub 0 is 1. I'm going to do the derivative of my polynomial, which is c sub 1 plus 2c sub 2 plus 3c sub 3 x squared plus 4c sub 4x cubed. I'm going to evaluate that at 0, giving me c1. I'm going to do the derivative of my function, which is negative sine, evaluate that at 0, which is 0. Now look what happens here. I set my polynomial value equal to my function value, and I get c sub 1 is 0. What I'm now going to do is take the second derivative of my polynomial, the second derivative of my function. Here's the second derivative of the polynomial. The derivative of negative sine is negative cosine. Evaluate them both at 0, set them equal to each other. C sub 2 is a number again. It doesn't zero out. It's negative 1/2. So pause as we go here. Now I'm going to do a third derivative. Third derivative of my polynomial is here. Third derivative of my function is sine. Evaluate them both at 0, because that's where I'm centering. Set them equal to each other. C sub 3 zeroes out again. So now do the fourth derivative. And notice I'm writing these so that the factorial will naturally come out. So then I do my fourth derivative of my polynomial, the fourth derivative of my function, set them equal to each other, and I get this. What I'm going to do is write my fourth coefficient as 1 over 4 factorial. Third coefficient is 0. Write my second coefficient as negative 1 over 2 factorial. First coefficient was 0, and c sub 0 is just 1. Technically, it's over 0 factorial. So what I can do is personalize my general polynomial for cosine. And cosine of x, the fourth polynomial approximation, is c sub 0, which is 1. C sub 1 was 0. C sub 2 is minus 1 over 2 factorial x squared. C sub 3 is 0. C sub 4 is 1 over 4 factorial x to the fourth. It'd be minus, or actually the fourth one would stop there. If it was infinite, it would keep going. So your homework for this video is to derive from scratch these three, just like I did finding the derivatives, and p sub 4 of x.